How are you today? Okay, to remind you what we learned previous time, I described in previous lecture state space representations, and we went through explicit representations for CISO systems, for MIMO systems, discrete time, continuous time systems. I showed all these block diagrams that you can get from these representations. We learned a little bit about stability. We discovered surprising fact that eigenvalues of the system are actually poles of the system, which is exactly the same thing. And this means that now we will be talking only about eigenvalues of the system because this is what you get from the matrix A. So taking eigenvalues of the matrix A, they will be poles of the system in open loop, in closed loop, when you will have the controller closing the loop, and so on. So we will just deal with these eigenvalues all the time because they will be poles of the system. As we know, poles of the system have relation to performance of the system and stability of the system. So we talked about stability of the system and stability for continuous time system. I remind you, this is when all of your poles in the left semi-plane, in complex plane, in complex domain. And this means that the real part is negative. For discrete time systems, they all need to be in unit circle, which is circle with radius 1 around the origin. Okay. And same thing I'm saying about eigenvalues of matrix A. So eigenvalues need to be on the left or in the unit circle, depends if it's continuous time or discrete time for stability. And I'm talking here about asymptotic stability. For Bibo stability, you still need transfer function or some other additional tools to understand its system as Bibo stable. But for asymptotic stability, you're just checking eigenvalues. That's what you'll get before cancellation. All right, so today, we also that example, computed that zero input response, and we discovered that for that not asymptotically stable system, that response is converging to 0, which is very interesting fact because you need to remember that not all asymptotically unstable systems always diverge. You might have convergence in asymptotically unstable systems for a particular initial conditions. So it can have 0 input and particular initial conditions from which it converges to 0, like stable in a sense, but it's still asymptotically unstable because for asymptotic stability, it needs convergence from any initial conditions. And pay attention that for linear time invariant systems, if system is asymptotically stable, it converges from any initial conditions. And you can start them anywhere you want, in +1 million or whatever. You can choose any numbers you want. In practice, it will be different. So in practice, all of the natural systems will be only locally close to linear, which means only for small deviations from equilibrium points, they will be stable or unstable. So you'll be able to use that type of theory. You cannot put 1 million volts as input to your system and expect it to behave linearly. Okay, this will not happen in reality. Any questions so far? Okay, just to remind you that rank of the matrix, and this is what we will be dealing with, is rank of the matrix, is number of linearly independent columns or rows in the matrix. And this number is the same for rows and columns. So if you have linearly independent columns, m of them out of n, then you have the same number of rows and columns which are independent. Also to remind you something from linear algebra that I probably haven't mentioned when we went through the rank and so on, is that if you have more than n vectors of order n, which means every vector is like size n, and you have more than n of them, that set will always be linearly dependent, which means the maximal number of independent vectors that you could have is the size of the vector. Okay, which means n vectors, which are independent, always spanning the entire n-dimensional space. So you can get any vector in that n-dimensional space as linear combination of n independent vectors, right? So you can build that as linear combination of n independent vectors and any other vector of the same size. This is a theorem in linear algebra. Okay, but if you have like n plus 1 vectors, at least one of them is dependent, right? So you need to be aware of that. So for example, if you have non-square matrix, the rank is decided by the smallest dimension. So if you have, for example, like 2 rows and 50 columns, rank cannot be more than 2, because you have only 2 rows, right, in that matrix. This is what you need to remember. This is a theorem that rank also of multiplication is always smaller than minimum of the ranks of each one of the matrices. That's also important to remember. And additional things that we'll be using a lot, especially for CISO systems, is that if A is of full rank, which means the rank of the matrix A equals to n, this also means that determinant is not 0, because if matrix is not invertible, the rank will be smaller than n. Okay, so you will have some dependence. If all of the vectors in the matrix, all of the columns of the matrix are independent, this means that determinant is not 0, and the matrix is invertible, practically speaking. All right, this is about rank, and why do we need rank in general? Because of that important theorem, and this is controllability property of any control systems, which is fundamental for understanding what you can control and what you cannot control in particular systems, given your matrix A, B, C, D, okay? So controllability means that you can take the system from any initial state to any other final state in given finite time, okay? Or given number of steps if it is discrete time system. So system is controllable if you can start with any point, x0, and get to any xf, which is x final state vector. So you could get all kinds of trajectories to get to that vector, okay? But you can design such inputs to that system that it will move by that n-dimensional trajectory from one point to another point. Also, this means that you practically can design controller, state space controller, which will take your poles in closed loop anywhere you desire. So you will be able to move open loop poles any place you wish. So you tell me where you want them to be, and I will give you controller which moves them to that place if the system is controllable. If the system is not controllable, then it generates new kind of issues. So if system is not controllable, it still could be stable or stabilizable, but you cannot move all of the poles. You can move only a subset of the poles. This is what it means. All of the poles which will be canceled with zeros in transfer function, you cannot move them because they are canceled, okay? And this system will not be controllable or will not be observable. We will talk about that later, like how we deal with all of these issues. We'll have separate lecture on how to deal with not controllable systems, how we still can design some controllers for them, okay? So it's very important to understand that controllability means both. You can move from any state to any state, and also you can design any controller, not any controller, you can design a controller which is putting poles anywhere you want. That's what controllability is. And then we have a very nice theorem here, which allows you to detect if system is controllable or not. And this theorem states that the system is controllable if and only if a particular matrix has full rank. This is what it says. And this is that matrix. So you have column B, then you have column which is A times B. And pay attention that matrix A times B is still vector of the same size as B, right? And then A squared B also vector until you get to n vectors. And the last vector will be A to the power n minus 1 times B, okay? So you put all of these columns, you get matrix, you check rank of that matrix. If rank is full, which is n, then the system is controllable. You can do whatever you want with it. You can design controllers that move your poles anywhere you want, okay? If it is not full rank, then you cannot do that, and we will deal with that later. What can we do still with that type of system, okay? Now, I think that I mentioned and I focused previous time on particular formula, okay, which is explicit solution for X and explicit solution for Y, especially for discrete case. And the explanation for the things is coming from that formula, okay? If you remember, we had that type of solution for X, explicit solution for any state X for discrete time system, this for continuous time system. So pay attention that this matrix, these columns, okay, these vectors appear here, which means that the solution is always linear combination of these vectors. This is what it is. And this is exactly what the thing is saying. So the second part of that theorem states that any place that you can get from particular state is spanned by these vectors, which are columns of that matrix. And that's exactly what this thing is saying. Okay, so you can find such coefficients u, which are just a bunch of numbers, right, in time, that you'll have linear combination of that type of vectors. That's it. So you'll start with some initial conditions x0, and then you will move only in directions of these vectors, okay, or linear combination. So if they are not spanning the entire space, you cannot get to all of the points in the space. You can get only to points which are spanned with that linear combination of these given vectors. That's it, from your initial point. So you can go only in particular directions. You are limited in number of directions where you can continue from given x0, okay? So the number of angles is limited in a sense.
In that case, the word that we would use is not controllable. We would use
It's not controllable,
finite. Like, is there a word for that?
non-controllable.
Non-controllable.
Yeah, the system is not controllable then. All right, so this is what this theorem is stating, and this is the explanation where it comes from. Same thing basically here, because this is infinite series of matrices of a squared, a cubed, added together as a series, and you multiply that by b, so you get practically the same thing, just infinite number of terms, but same thing, and you don't need more than n. So here you have n columns, and as I stated, if you put more than n, it will definitely become dependent, so there is no sense to add more to it. This is the minimal spanning set, okay? Also, you can show that they are kind of independent, if all of them are independent, so this is how you build it, all right? By the way, you can change the order, but it's not very convenient. You can change order of the column, it doesn't matter in which order it goes, because determinant of that entire system will still be the same if you switch in the order. It still will be non-zero. If it is non-zero for that particular matrix. But here we have multiple different additional interesting questions, because you have additional terminology that people sometimes use in that theory. For example, reachability, because we are talking about like what states we actually can reach. And the idea of reachability is where you can reach from zero state. Like if your x0 equals to 0, like origin of your n-dimensional coordinate system, where you can get with your system. So if system is controllable, you can get anywhere. So it's obvious. But if it is not controllable, you will be able to get only to the span of these columns of the matrix from 0, right? So in LTI systems, reachability and controllability practically are the same. And that's why I'm not differentiating. And reachability matrix will be exactly the controllability matrix. But reachability might be very different for nonlinear systems. So you might have nonlinear systems for which states that you can reach from 0 are not the same states that you get for controllability, which is a different kind of problem, which is asking like what initial states, from initial state, like where you could reach, okay? A little bit different formulation. So for nonlinear systems, it will not be the same, but for linear systems, we just assume this is exactly the same thing. Another question, how actually to get from state 0 to state F, final state, right? And for that, you have formulas. Formulas are pretty simple, more or less theoretical. Not many people are actually using that for any practical purposes, but you just need to be aware that they exist. All right, so formula for discrete, for continuous time case looks like that. So it's inverse controllability matrix, that particular matrix B, A squared B, and so on. So inverting that matrix, multiplying by exponent of negative AT final state, which is at final time, times vector of x finals that you want, minus x zeros that you have, which is initial state, times deltas and their derivatives. And that's why it is theoretical. You cannot really build function which is delta. And you will arrive to the final state in 0 time, which is very interesting. So continuous time system can get from one state to another state in 0 time if you would have access to delta functions and their derivatives. Okay, but with these functions, you actually can get, because delta is only at 0, right? It's like spike at 0, it's like impulse, and then 0 everywhere else. So starting with the zeros and derivatives of that 0, and you put in like n of them at the same 0 time, and you get to any other state. System kind of jumps immediately to some completely different state, which is defined by you as well, which is xf. But for discrete time, you can get to the same point that you want in n steps. So if your system is n by n, you get to the final state in n steps. Here's how it goes. You have, first of all, input 0, then you have 0, 1, 2, 3. So this is what you get. You put your vector u of k, which is practically a function of time. You have different kind of numbers at different times. And you're starting from bottom up, which means you're building that vector as u0, u1, u2, u3, until you get to u of n minus 1. Total, you will have n inputs, right? So the vector is size n. How to get that vector? Very similar formula to this one. So you get inverse controllability matrix of your system times final vector minus a to the power of n times initial vector. That's it. You will get all of the steps from bottom up, all of the inputs that you need to give to your system to achieve that state, xf. Any questions on that formula? So again, this is more theoretical thing, and we are in the course of modern control theory, if you don't remember, okay? So this is theoretical thing, what kind of inputs you need to get your controllable system from any place to any other place. And pay attention that this will exist only if the system is controllable, right? Because otherwise you cannot invert that matrix if it is not full rank. So this matrix will be invertible only if you have full rank. Okay, additional thing, which is called observability. Now I will describe the problem that we will eventually have, and we will work again. We'll have a special lecture on observability and designing observers and getting later to Kalman filters, which are also observers. So here's the problem. You have your input u, you have your outputs x, then you multiply that x by matrix C, and then you get your y. But in reality, you not always have access to measurement of all the states x, right? So if you remember, we defined x as all kind of states inside the system. It could be currents, voltages, powers, whatever, or mechanical moments or angles, or it could be all kind of things, or could be combination of all of them, okay? It could be some mathematical complicated formula to define particular state based on the variables of the system itself. Like it could be, I don't know, how much air passed through the airplane engine, okay? This could be state of the system, how much pressure, air pressure you have in the engine. That kind of things you cannot even measure, okay? Or your sensors will be super expensive to measure that kind of thing, okay? But controllers that we will be building will connect to the states, which means we will take the state, multiply it by all kinds of numbers, and return it back as feedback loop. This will be our state controller. Which means that to design state space controller, you need access to all of the states. So you need to measure all of them somehow. And sometimes you just can't. It's a problem, right? For natural design of controllers. If you cannot measure something, you cannot connect wire to it, right? You cannot actually return the feedback loop. You don't have access to it. You cannot really measure it. And it could be true not only for mechanical systems, like if we are talking about brain, you can measure some of the points in the brain, but some other points in the brain you cannot measure. So you cannot return the loop from the points that you cannot measure. So you need to estimate them somehow. You need to measure them from other things that you have. And the access that you have is outputs that you actually measure and inputs that you're actually giving to the system. You're introducing some inputs so you know what that thing is, like some pulse or step or whatever input you give to the system. And you have output, which you actually can measure. So you put sensor on it of some kind and gives you some voltage as output, for example, or some numbers in the computer running as a function of time. The question is, can we take U and Y and knowing the model of that thing, like the black box, computing X from input and output alone? Like, can we estimate X's from U and Y? This is a problem that we are trying to solve in observers in general. And the observability property means, like, if system is observable, it means yes, you can, practically. So you can take U and Y, and you can compute X from U and Y. And then you can, that computed thing, you can connect it to controller and return it back to the loop. This is how it works. So observability means, is it possible to compute the initial state x0 from inputs and outputs given in time? Because this is where you have access always. Okay? So you need to have like all the matrices, obviously, A, B, C, D. You need to have inputs and outputs, like input you design and output you can measure with your sensors. And then given all of the data that you have, you can compute x0. This is what observability means. And very nice theorem, how you actually define or how you decide on observability. The system is observable if and only if particular matrix is of full rank. So we will have, again, the same kind of thing, but in that matrix, you will have rows now. So rows will be C, CA, CA squared, CA cubed, and so on until you get to the nth row, which is C times A to the n minus 1th degree, okay? So it's like rows now, not columns, because C is row and CA is row and so on, okay? Then the system is observable if this specific matrix is of full rank. This is what we know, which means that you will be able to trace back to x0 the entire trajectory of all of the x's, okay, that you have in time. All of them are a function of time, of course. And all of the states that you can reconstruct, if this is not full rank, are spanned by rows of that matrix, which means everything that you can compute will be again limited in particular subspace of the entire n-dimensional space. So you'll be able to, like if your trajectory is within that subspace, you still can get all of it. But if it is kind of leaving that subspace somewhere else, then you cannot replicate it back. You cannot really compute all of the x's for your entire system, unfortunately, and might give you wrong x values. This is what it means. You will not be able to compute it. Any questions?
Is it a column vector only because so that you will be able to multiply it with the input vector? The observability where this vector.
So this is matrix, okay? So this is n by n matrix.
Yeah.
But it's built from rows of C, CA, because if you're thinking about dimensions of C, C is 1 by n, right? So it's like row vector. So you multiply that by matrix, you again get row vector of the same size. If you multiply it by a square, it's again row vector of the same size. So building these rows, and this is what this matrix is. Okay. Now for MIMO systems, it could be actually matrix. C might be matrix, right? So multiplying that matrix of the dimension by A, you get matrix of the same size. So you have multiple rows. So this thing will be not single row, it will be multiple rows by n. Depends on number of outputs, obviously. Okay. And same thing here. So it will be not rectangular and not square matrix anymore. It will be kind of long matrix with many rows and m columns. Okay, so it will be m by n, like long matrix. And we will have question like how you define then observability for that type of matrix, because here you cannot compute determinant anymore. You cannot say like it's full rank because determinant is not 0. As simple as that. So you will have all these questions. We will talk about that a little bit later, but you have all of that, all right? So before we get to these interesting questions, I want to define minimal systems. So minimal systems are systems where you have no cancellations between numerator and denominator of the transfer function. So it's everything's canceled. Okay. You don't have any zero and poles which are canceling. This is minimal system. So this representation will be both controllable and observable. So if the system is minimal, it is controllable and observable. It's very important to remember. And if and only if. So if system is controllable and observable, it's also minimal, which means that if you compute a transfer function from controllable and observable system and you get cancellation of zeros and poles, you made calculation error somewhere. Okay, it cannot cancel. All of them will be different, poles and zeros. Any questions on the minimal systems? I hope you at least heard about that term in controls 1 somewhere, maybe. Minimal systems where you have no cancellations between zeros and poles, but that's fine even if you don't. All right. So what happens if you do have cancellations between zeros and poles in your transfer function? So you have 3 different options here then. System could be not controllable. I mean, if no cancellation is controllable and observable. So what are the options if it is not, right? So it could be not controllable or not observable or both not controllable and not observable, right? So these are the 3 options that you might have. Nothing else could be. So you need to be aware if you have some cancellation, definitely at least one of these matrices will not have full rank. Maybe both will not have full rank. Okay, that's what you know about the system just by looking at transfer function of the system. Also, it's important to remember that observability is defined by ability to estimate x0 from inputs and outputs. But if you can estimate x0, you can estimate all of the x's to the final state. x0, x1, x2, x3, x1 million, whatever. This is always true for all of the systems. So the definition says you can estimate x0, but essentially you can estimate all of them because you know the entire trajectory practically back. You compute the entire trajectory back, so you can have all the points on the trajectory if you can get to the first point. Okay, this is what it means. To compute observability matrices or controllability or observability matrices, you don't need powers of matrix A at all. This is just trick for computations. Like don't compute A squared, A cubed, A whatever. Here's how it goes. So you need vector B for controllability matrix, then AB. So you multiply matrix A by vector B. You get another vector. Okay, this is a second column in the matrix. Now you need A squared B. How can you compute A squared B without doing A squared? Because A squared is like n by n matrix times n by n matrix is like tons of computations. You don't need any of it. How would you compute A squared B instead of computing A squared first and then multiplying by B? What is A squared? Is A times A, right? But AB you already computed in the previous column. So just multiply it from the left by A. That's it. So you multiply A by AB, which is the previous vector, and you get A squared B. Again, multiply A by the previous vector, and you get A cubed B. And so on. So you're kind of moving that from left to right. And you get multiplication of powers of A by that vector B, where you just each time multiplying by A from left to get whatever you need. Next column. You don't need to compute powers of A. Any questions on that? And now we will start with some interesting example. And this example tells you how to compute transfer function, which we've seen previous time. And just to make it more interesting, I will use different formulas this time for computing transfer function. You can get the same, so use other formulas. Then you need controllability and observability of that particular system and telling me if the system is minimal. Which will be pretty simple. And then just to find how to get to a particular final state. And I want to show you something relatively interesting from the computation itself, because the solution will be a little bit weird. But we will see. Okay. So let me try to get to another screen here. Recording the board. So I will write all of these matrices on the board that you will have them. So matrix A 0.05, and all of the elements are 0.05. Okay. B equals 1, 0. C equals 1, 0. Thus our system D equals to 0. For simplicity, we will almost always assuming D equals to 0, not to carry it. Okay, and actually many practical systems have D equals to 0. All right, so we want transfer function of that particular system. If you remember transfer function G of Z, this is discrete time. Discrete time system, which means we are working with Z, not with S. The formula is exactly the same, so it doesn't matter. That will be C, ZI minus A, inverse B. And it should be also plus D, but D is 0, so ignoring that part. Okay, so let's compute that. It will be C, which is 1, 0, times matrix. So Z times 1, Z minus 0.05. 0 minus 0.05, so it will be negative 0.05, negative 0.05, and again Z minus 0.05 inverse. This is Z times I minus A. Okay, and times 1, 0. Okay, so it will be 1, 0 times, so it's 1 divided by determinant of that thing, which will be Z minus 0.05 squared, minus this one times this one would be 0.025. Something like that. 0.005 squared. So it's this one minus this one times this one will be minus this one squared. And since minus by minus cancel.
Will there be another zero after decimal?
Another 0? Why another 0?
The 4 decimal.
So 5 by 5 is 25, so it moves 1 to the left. It should be like that. Calculator. Okay. All right, so how we invert that matrix? So we switching these two values and making minus and minus here, right? It will be same value Z minus 0.05, Z minus 0.05, here's plus 0. Okay. So this thing will be equal to 1, 0 times the same thing times. So when you multiply by 1, 0, you take this value times 1 plus 0 times that one, so it's Z minus 0.05. And this one times 1 minus 0 times this thing, that will be 0.05. Okay. But since eventually we are multiplying that thing by 0, so we don't care about that part. So it will be 1 divided by that same thing times Z minus 0.05. Something like that, right? So when you're opening that algebraically, you get 0 Z squared as a result, minus 0.1 z. Here we have z minus 0.05. This is the transfer function. And we calculated the square was 0.05.
Yeah.
Is that correct?
0025.
0025. Okay. Just like that, right?
0.00.
0.00.
0.00.
Zero.
Okay. You get that. Okay. And regardless of what formula you use for that, you can use all of the three formulas to get the same thing. Any questions so far? So now we need to compute controllability and observability properties of the system. So controllability matrix will look like that. First of all, B, it's 1, 0. And then the same times that thing. So it's 0.05 times 1, 0.05. And again, 0.05. That's our controllability matrix. Questions from that? This is just A times B vector, which is that times 1 and that times 1. Is it full rank? What is the rank of that matrix? For 2 by 2 matrices, it's very simple to check. I mean, you can compute determinants like 1 times something minus 0. So 1 times something is not 0. So it's definitely 2. Full rank. Okay, so it's controllable. Same thing with observability. We start with C, which is 1, 0. And then we're multiplying C by A. So it's 1 times 0.05, it's 0.05. And again, this one times the second column, 0.05. What is the rank of that matrix? Rows are independent, clearly, so it's still 2. So it's observable. So system is controllable and observable. What does it mean regarding the linearity, the minimality of the system? It's minimal. You also can see it from here. You have no cancellation of zeros and poles. Clearly, you have pole at 0, and then you have pole at 0.1, but your 0 is 0.05. Right, so they different. All of them. They do not have any cancellation of zeros and poles, so it's minimal. Any questions so far? Okay, so now we want to get from particular initial state to particular final state. And our initial state will be at 0. See, initial state we have 1, 2. And we want to get to the XF, which is like 2, 2. Right? So we want to find U such that it will move from that state to that state. So let's see. And we are actually promised to get there in maximum 2 steps. Because you have formula how to find 2 inputs, U0 and U1. And this U of K will be practically U0, U1. These are the steps. We're computing them using that formula, which is controllability matrix inverse times xf minus a squared x0. So here is like nth order of the system. So let's compute that. So you need inverse that matrix. Times, here you have the vector xf, which is 2, 2, minus 0.05, 0.05, matrix A squared, and 1, 2. Okay, so this is what you need to compute. It will not even go through the algebra, it's just numbers. Use MATLAB for that or whatever, by hand if you wish. The answer would be more interesting here. And the answer is 0.39.7. Which means in the first step, which is 0 time, you're giving it input 39.7. At the second input, you're just giving it 0. Like nothing, no input. And now the question becomes, tricky question is, like, can you get from that state to that state in one step then? Because second thing that you are giving is practically 0, which is no input. Is it getting to the state 2, 2 in one step after giving that thing? What do you think?
Like introducing a delay.
Hmm?
Is it like introducing a delay in the system?
Delay? Why delay?
Like, I'm just telling the
You don't have delay in the system. It's just inputs that you are giving. You're giving particular numbers as input of your system, right? At particular times. So at time 0, you are giving it 39.7. At time 2, you just not giving anything. 0. Okay. Does that mean that after the first step, you already reached the state, so you don't need to give any input? You will get used to that, because if I'm asking questions, they are definitely tricky, right? So the answer is obviously no, but
Can you say, can you say that like it is reaching that state because you didn't give any input at the end?
so here's the thing. So 0 is input. It is input. It's wrong to say that you're giving no input. If you will not give 0, it will not reach that state, okay? So after the first input, it reaches completely different state. And then you are giving 0 input, and then it reaches that state. And you actually can compute that by hand in that particular example, because this is just system 2 by 2. And you can evolve that system just by multiplying by x here, right? So you can start with that x, you can multiply that thing by that thing, plus b times that 39.7, and you'll have first step of your system. You will have the next x, xk plus 1, right? Which is x1. Then you will have state which is not that. It will be different, okay? Then that different thing you'll put again here, multiply a by that new state, x1, right? Plus b times 0, which means in the second step, you are just not using b times u, but you're still multiplying by that matrix, okay? The previous state. And this will change it to that state, that multiplication by matrix A. Just in the second step, you are not using bu. That's it. You do not use input, because input is 0, you're multiplying by 0. But you're still multiplying by matrix A, which is kind of rotating the vector in a sense, right? It's kind of moving the vector somehow. So you still need that 0 input to get to that value, right? Questions? All right. Now we will talk about similarity transforms. And the question becomes, how many different systems might be equivalent, at least in some sense? So we can define some invertible matrix T, which we will call transform, similarity transform. And we can define new type of vector X based on the original vector X as just multiplication by T inverse. Okay, and T is just any invertible matrix, like pick any matrix you want. What I'm trying to show, and also equivalent, you can say that X equals to T times X tilde, and tilde is a new state. This is what I want to show, actually. That similar systems, which are defined through that relation of just multiplication by any invertible matrix, have very nice properties in common. And one of these properties is having exactly the same transfer function, which is extremely important, obviously, for systems, right? So no matter how you define the matrix T and multiply by the T inverse, you get completely new state. And each time it will be different state for different matrices T, obviously. You will get system which has exactly the same transfer function. You'll have completely different state space representation, the transfer function, but all of them will be equivalent transfer function, same poles, same zeros, same eigenvalues, same, okay? And I will show why. Let's develop that a little bit just to see how stuff works in that sense. All right, so let's say you have that state space system which is defined by matrices A, B, C, D. I want to find equivalent matrices A, B, C, and D with tilde, which would describe my new system, okay, with that new defined state with tilde, which is just multiplication of previous state by invertible matrix of some kind. Okay, so let's see how it goes. First of all, X dot, which is just taking dot on Z, would be T times X tilde dot, right, by definition. So that's what I'm writing here. So it's T times X tilde dot. Now, A times X will be A times T times X tilde. So I'm converting everything into tilde now, right? That's what I want. So it will be A T X tilde plus B times U. I haven't changed U, so it stays as is. All right. Same thing for Y. So Y is S C times X, and X is T X tilde. So I'm just substituting that here, plus du, and du hasn't changed. So that's my new system. And now I want to write that system for X tilde dot. Like, so what is X tilde dot? Because this is my new state space representation. I want something dot equals everything else. So how can I get there? I'm multiplying by T inverse both sides to get rid of it on the left. And I know that T is invertible by definition because I stated that as T inverse X, right? So it's invertible matrix. So when I multiply both sides from the left by T inverse, I cancel that T. But here I have T inverse AT, and here I have T inverse B, right? This is what I have. So I have that new system like that. And you can think about that entire thing which multiplies X as my new A tilde of some kind. And this is my new B tilde. And this is my new C tilde and D tilde. Right? So this is new system which looks exactly the same as the previous system. It's some matrices A, B, C, D, but with tildes, which look exactly the same structure, right? It's still like X dot equals AX plus BU, and Y equals CX plus DU. Same structure, same linear system, but for a different state variable. Now, this is completely equivalent system in terms of transfer functions. This is my claim, right? And this is why. I'm showing you now why this is the same transfer function. So let's say you have that new G tilde transfer function, and I want to show that this is the same as G transfer function for that particular system after I substitute all of these matrices instead of these matrices, okay? Everything will cancel out somehow in the middle, all of the T part. So let's see how it goes. So this is the formula that we are using, right? It's like C tilde times SI minus A tilde, or it could be Z, which is discrete time. Inverse times B tilde plus D tilde. So let's substitute all of these definitions that I have here. Okay, so C tilde is C times T. So I'm substituting it here. Now, Si minus A tilde is T inverse AT. So I'm substituting that thing here, right? B is T inverse B, this one. So I'm substituting here, D is the same. Okay, so far? I just substituted all these new matrices instead of old matrices. And what I want to show that this is equal to C times Si minus A inverse times B plus D. These original matrices. That's what I want to show. And then both transfer functions will be exactly the same. So here's how it goes. First of all, I can multiply that thing from the left by T inverse and on the right by T. I'm not changing that first term, right? This is the same trick I'm using already multiple times. I'm multiplying by inverse of the matrix and the matrix on both sides, so they cancel because you have I between them. So I is not changing the matrix. And multiplication by constant, you can take it out of the computation, right? Of the parentheses. So I haven't changed here anything, but now I can take T inverse from the parentheses to the left and T from the parentheses to the right. So this is what I will get. So I'll have T inverse times Si minus A times T, all of that inverse, which is that inverse, okay? And here I keep the same thing. Okay, so far? So it's just a little trick that we are using all the time. But pay attention that when I'm doing inverse of multiplication of matrices, these are matrices in inverse order, each one of them inverse. Okay, remember like AB inverse is B inverse A inverse. Okay, this is for multiplication of matrices. So all I need to do is to take that matrix first inverse, then that matrix inverse, then that matrix inverse. But matrix inverse inverse is the original matrix, right? So T minus one is T. So this is what you will get. So you'll get CT times that thing inverse, which is T inverse. This will cancel. Then you have the second matrix, and then on the right you have T minus 1 inverse, and then inside you will have Z matrix inverse, which is the original matrix T, also will cancel. And then you have B plus D, which gets you back to the original transfer function. Okay, so all of the T matrices canceled out somehow. Okay, lucky us. The idea is that similar systems, which are defined that way, and you can define as many as you want, all of them will have exactly the same representation in frequency domain, which is transfer function. Same impulse response, same differential equation, same everything, practically same system. You just have different representation for the same system, because all of the properties that we learned in control systems 1 were dependent only on transfer function, okay? So the only difference here is initial conditions, which means that if system is stable and after some transient response, you'll get exactly the same outputs for all of the systems. All right? So the only difference is how you define initial conditions to that system. Other than that, they all completely equivalent in terms of their zero state response. All right. So they have obviously same eigenvalues, same transfer function, same controllability, observability properties, minimality properties, and so on. Any questions? So it's a very nice way to represent systems, right? You choose any matrix T you want, make your system look very convenient for your processing or controller design or whatever you need to do. Just find your convenient representation for your system by finding the right transform. And then everything will be nice and smooth and easy to compute. All right, a few questions. Has this? Yes.
So let us say you started a system at initial point and you reach the final point.
Mm-hmm.
And from there you have one more final point. Let us say that the first initial final point becomes the initial point.
Right.
And there is a new final point. Mm-hmm. So can we consider both those systems as similar systems if they are observable and like if they are controllable and if they have the same eigenvalues?
I'm not sure that I completely follow your question, because you're saying these properties are independent of particular trajectories of states, okay? So you are saying that your system has exactly the same transfer function, which means that response after all the initial responses of like transient responses from initial conditions it will converge to the same values if the system is stable and moving on particular stable trajectory, right? So for all of the systems, they will move on the same trajectory. It doesn't matter if you reach particular state, you cannot redefine now from the middle of the way the system into a different system, because for that system, state will be completely different. You can translate it into different state. So your x0 for that system will not be the same x0 for the other similar system. So you need to translate it by multiplying that by t inverse, right? And then if you start with that new initial condition, then you continue on the same trajectory. Okay? But they kind of have different state definitions. It's like, think about that the following way. Let's say you define first state as current and second state as current dot. Can you switch between x1 and x2? Will it change the real system, right? So you'll just switch equation number 1 with equation number 2. So everything which you call x1, now you call it x2. And whatever you called x2, you call it x1 now. That's exactly the same system, right? You just renamed the variable, right? But initial condition also will switch, right? It will be different initial condition. So you just renamed the variable. It still will be the same system. So that switching between rows, for example, you can do that with multiplication by a matrix, right? Which is like cross diagonal, like 1, 1, 0, 0, for example. It just switches the names of the variables, nothing else. As one example of invertible matrix, right? 0, 1, 1, 0, 1, 1, 0, yes. That type of matrix. So you can do that, but you need to recalculate the initial point. All right. All right, so if the system realization is not controllable, does it mean that all of the system realizations are not controllable? So you cannot make it controllable, period. Is it true? That would be sad. The answer is no. You can find still controllable realizations for any system you want, but then you definitely will lose observability. This is the same. So you get something, you pay for it, okay? So system could be designed as controllable. If controller is more important to you, to design the controller, you can make the system controllable with specific realization. But cancellation of poles and zeros will not disappear anywhere, right? So it must be then non-observable, which means that you will need to measure all of your states, which sometimes possible, sometimes not. And same thing with observability. Not all definitions of the state will be non-observable. But if you require observability, which means you just cannot measure any of the states, you can measure only output and input, and you need to compute all of the x's, you will lose some of the controllability properties. You must. You cannot have both if you have cancellation between zeros and poles, right? So this might be a problem for some designs. For some other designs, it's not a big problem, especially if your cancellation is of stable poles and zeros. If it is unstable pole and zeros, then you are in trouble. And you shouldn't design your systems that way. But if it is stable cancellations, that's okay. It's not that bad. All right. So how we check controllability or observability of MIMO systems, where you have non-square controllability and observability matrices? What is the approach? You cannot compute determinant. What should you compute? By definition, you compute rank. It's still true for any non-square matrix. You can compute rank, how many independent rows or columns you have in the matrix, okay, regardless of determinant. And it's more complex. I'm not saying that this is easy. To compute number of independent rows, you need to solve system of equations, blah, blah, blah. It's more complicated. And this is why for MIMO systems, people do not do that by hand. And final question that we almost answered already. How many possible representations for state space systems you might have for a given transfer function?
Infinite. Infinite kind of like we got state.
Yeah, as many as you want. Infinite number. You can have infinite number because you can choose any random invertible matrix and generate new state definition, okay? And all of them will have the same properties. So have infinite number of possible representations in state space. And now finally we move to the most interesting question, how you can convert one type of representations into another. And we struggled a lot to convert transfer functions into state space. We needed definitions of states, and then we computed all of these things, derivatives, and like moved a lot of algebra left and right. No needed any of it anymore, not after this lecture. All right. So here's how we do that. There are multiple canonical forms which represent particular types of transfer functions. And they include controller form, observer form, diagonal form. You can use any of them. All of them are equivalent, give you exactly the same transfer function. And they have obviously similarity transform between them if they are controllable and observable. So it's very easy to do. And here is the first one. So the first one is canonical controller form. I think in math it's also called companion form, something like that. But we call it canonical controller form. So given any particular transfer function like that, so you'll have coefficients b1, b2, b3 of the zeros polynomial, and then you'll have coefficients say 1, 2, 3 through n for that polynomial, for denominator, for poles. And you also will have free coefficient d. And pay attention that this is strictly proper function. Strictly proper means you have less zeros than poles. If you have exactly the same number, then you have that coefficient, right? So if you divide like polynomial of order n by another polynomial of order n, you can write it as constant plus different polynomial divided by the same polynomial of order n. But this different polynomial will be n minus 1 order because you took that constant out of the rational function. So you can always bring it to that shape, okay? So if you have same number of zeros and poles, first bring it to that shape before you implement it. Otherwise, you cannot do that. So just remember that you have coefficients b, coefficients a. This is your realization. Your parameter d, which is matrix d, will be that d. This is that constant number which is coming out of the transfer function. Here you will have negative, first row of the matrix A will be negative, all of the coefficients of that polynomial. Like minus a1, minus a2, and so on, until you get to minus an. All of the negative ones. Second diagonal, like below the main diagonal, you have diagonal of ones. All of them just diagonal of ones. Everything else, zero. This is matrix A. This is companion form of the matrix, okay? So you put in all of these coefficients with minus. Here, second diagonal below the main diagonal of ones, everything else zeros. This is matrix A. Matrix B is always 1 and zeros, as many as you need for order n. Okay, it's like 1, 0, 0, 0, 0, 0, whatever. Matrix C are coefficients of zeros. That's it. This is your form. If you find transfer function of that thing, it will be that. So this is one simple form, okay? So you can always realize any system as controllable using that controller form. And that's why it's called canonical controller form. It's always controllable. The controllability matrix is invertible, and I even computed that explicitly, how it looks like. So it will look like 1 on the main diagonal, zeros below that main diagonal. So it's triangular matrix, upper triangular matrix, okay? Here you have coefficient a1, 2, 3, 4, 5 to n minus 1, because you have like n minus 1 columns left, right? And then you copying that by diagonals, all of the coefficients, okay? This is how this matrix will look like, standard way to represent. That transform to that particular state from any other state will look like that. It will be controllability matrix of your original state, which is your original matrices A and B, okay? Times that particular matrix. This will be that transform that we talked about, similarity transform, to that particular state. So it will take you from any given state, controllable state, to that particular state, canonical state. All right, that type of transform. Questions so far?
But in the, there's no B in the canonical, transform. Yeah, but in the matrix on the bottom, there's no B represented there. So
Yes.
when you have T is the original one times the matrix at the bottom. Why wouldn't that change depending on what the B is? Like the right side of that equation doesn't change depending on B.
Great
I'm trying to
question.
get in my head
It
why
will
that would be.
cancel out
It
in
cancels
the
out.
computation. Yes,
Okay,
it will cancel out in the computation, and you're getting into more deep and very interesting question is what effect of B will have on system in general, and what effect of C you will have on system in general. Because if you're thinking about state space and design of the controllers for state space, C is not involved at all, which means regardless of what coefficients you will have here for zeros, it will not change anything about your design of the controller.
and when you say C, you mean?
Yeah, C is like coefficients of B.
Yeah, the coefficient.
In that case, like coefficients of B are sitting in matrix C.
And D also.
And D also will not
Yeah.
participate anywhere in any calculation of any controller design at all. It will relate only to observer design and observer side of things, but we'll get to more specifics and more math behind it a little bit later.
Okay.
So I don't want to get into that right now. Right now, you just need to remember that you have way to represent state space system in controllable as controllable from any transfer function. Okay, so you have transfer function, just put all these matrices together, it will be controllable, representing that transfer function. Okay. Now you have dual problem, which is canonical observer form. This system will be always observable, representing exactly the same transfer function that we had before. Okay. And it will look like that. A observer, canonical observer, will be just transpose of the previous matrix, of that matrix. It's just you're flipping on the main diagonal of that matrix. Okay. And you're switching between these two matrices and just transposing them. And this is what you get. B of the observer will be transpose of the C controller state, controller form, and C observer will be just B transpose from the previous one. So this transpose will be here, and this transpose will be here. That's it. And inverse of the observability matrix now this matrix will become invertible always. Okay. Also very similar, flipping the previous matrix. Now the transform is a little bit more complex. Okay, so transform you can compute using that formula. Okay, from anything observable to that particular state. Okay, to get these matrices. And finally, we have diagonal form, which is the last form I will be talking today about. And diagonal form is extremely easy and extremely convenient to work with. Why? Because in that form, A matrix is diagonal matrix and still equivalent to the previous transfer function. Okay, so here's how it will look like. Here you have all of your eigenvalues. Practically speaking, you are doing just diagonalization of the matrix. If you remember what it is, right? Remember we talked about that a little bit in linear algebra. So you're diagonalizing your matrix A, and your eigenvalues are sitting on your main diagonal. And this is your new matrix A. And if you remember, diagonalization also was like T inverse times A times T. This is a similarity transform, okay? That's exactly what it is. But this particular similarity transform just diagonalizing the matrix. And how you get that transform, you put eigenvectors as columns of that matrix T, right? This is diagonalization matrix, how you get to that transform. This will be that transform. But how you get to other coefficients, okay? So other coefficients, you have infinite number of ways actually to get to other coefficients of matrix B and matrix C. Matrix D still will be D, so it's simple. But you need to do partial fraction expansion. Remember what that is? You write transfer function as sum of first order transfer functions, which means terms of that kind, some constant times S minus first pole plus some other constant divided by S minus plus other pole, and so on. So you write that as like first order transfer function, sum of first order transfer functions. And how you do that? You just combine all of them together with unknown coefficients, and then you find coefficients which match, or you have also formula for that. If you don't remember, let me know, I will give you the formula, okay? How to find all these coefficients. But here you'll have some coefficient, right? So you'll have some particular number divided by s minus first pole, plus some other number divided by s minus some other pole, and so on. The thing is that you can divide that the way you like, which means all you need that multiplication of beta by gamma will be that constant number that you have. How you decide on beta and gamma, it's your choice. It could be, for example, 1 for beta, so all of the beta might be 1, for example, and all of the gammas will be that particular coefficient that you have at the top, right? Or the other way around. Or some of them might be some other numbers, or it could be like 1/2 times whatever. So you can choose whatever you want. You have infinite number of possibilities here, how you choose betas and gammas. The thing is that their multiplication point by point should be these coefficients. Is it clear? All right. So system is minimal only if all of these multiplications are not 0, which means if any of these coefficients is 0, there's the same to say that you have cancellation between zeros and poles. Then one of these coefficients or more will be just 0. So that multiplication should not be 0 for all I, and then the system is minimal. Okay, system will be controllable if for all inputs, all of these betas are not 0. Okay, so if you choose all betas not 0, then the system will be controllable. If you choose all gammas non-zero, then the system will be observable. This is how it works. Questions? Okay, so we have no time to solve the last example here, but this is actually a very simple example. I will publish that online solution for that. I will publish video online to solve that thing. Any questions? All right, thank you.